And well, we are very happy to have with us in the Holo Club Ashish Shukla from the Perimeter Institute in Canada. Welcome and thank you for your time. He will tell us about effective field theory for hydrodynamics and analytic properties. Please.
Thanks for the introduction. So, as Jose said, I'll be talking about the EFT for hydrodynamics and its analytic properties today. So, this talk is based on a set of papers. The first part of the talk will rely upon a set of papers, which are these first three. The later part of the talk will rely on a paper which came out recently, about a couple of weeks ago, in collaboration with Akash, Pavel, and Adam, and some things that are still work in progress, but hopefully will come out soon. So let me start with an outline of the talk. I'll start with a basic introduction to what is hydrodynamics and what does hydrodynamics describe. So to this audience, I don't think I need to give this part of the introduction, but just to get things moving, I'll start with the very basics. I'll then move on to thermal equilibrium and the hydrostatic generating functional and talk about its properties. And finally, in the last part of the talk, I'll discuss hydrodynamic fluctuations, in particular, two major approaches to study these fluctuations out of thermal equilibrium, which are the stochastic hydrodynamics approach and the more recently formulated Schwinger-Keldysh approach. And in the Schwinger-Keldysh approach, which is the most, most successful, or so to say, the broadest of them all, I'll discuss about the analyticity of retarded correlators and how it is brought about by the KMS constraint that is inbuilt in the construction of the Schwinger-Keldysh effective action. I'll then summarize at the end. So let me start with a brief introduction to what is hydrodynamics. So hydrodynamics is the generic effective theory governing the behavior of physical systems near thermal equilibrium. The applicability of hydrodynamics rests upon the idea that we are probing a physical system at scales which are much longer than any inherent length scales of the system, microscopic length scales of the system, such as your mean free path or correlation lengths. Now consider a system which is in thermal equilibrium, and suppose we perturb it externally. This perturbed system will tend to relax back to the new equilibrium state. This process of relaxation to new equilibrium state will be governed by two types of variables broadly. These are the slow and fast variables. So the fast variables are the ones which relax back to the new equilibrium state very quickly, and the slow variables are the one, as the name suggests, which relax back much more slowly to equilibrium. And why is this so? This is so because the slow variables of a system are typically associated with the conserved quantities that are present in the system, such as the energy momentum tensor or a U1 current if there is a global U1 symmetry, etc. And these conserved quantities require actual physical transport to take place to relax back to the new equilibrium state. Okay, and this actual physical transport takes time, and that's why the slow variables, these conserved quantities, take time to relax to the new equilibrium state. Now, one can say that hydrodynamics is essentially the study of the slow variables that are associated with the physical system, these conserved quantities that are associated with the physical system. In this talk, we'll focus on relativistic hydrodynamics, which is applicable to systems that respect Lorentz invariance. And a classic example of this is, for example, the Quark-Gluon plasma that is produced at heavy ion collisions in laboratories like RHIC or CERN. Now, for such a system, the normalized fluid 4 velocity u mu, where mu is 0, 1, 2, 3 space-time indices, and the temperature T are the hydrodynamic degrees of freedom which we use to describe our system. Now, if there is an additional conserved U1 charge, then the associated chemical potential mu also becomes a hydrodynamic degree of freedom. Before I move on, let me just point out that my fluid velocity is normalized to -1. So it's a time lag vector normalized to -1. Now, given the fluid 4 velocity u mu, I can always decompose my energy momentum tensor or any conserved current that is present in the system in components along and orthogonal to the fluid velocity. So for example, I can write my T mu nu as some coefficient E times u mu u nu plus P times delta mu nu, where delta mu nu is the projector orthogonal to the fluid velocity, plus Q mu times u nu plus Q nu u mu. Q nu is called the heat current, plus tau mu nu, which is the symmetric, transverse and traceless part of the stress tensor. Similarly, I can decompose my current J mu as some function n times u mu plus some component script J mu, which is orthogonal to the fluid velocity u mu. Okay, So this decomposition of the energy momentum tensor or the U1 current is very generic. This has nothing to do with hydrodynamics. Where hydrodynamics comes is in the postulate that these functions that sit in these expansions, so this quantity E or P, etc., whatever coefficients that sit here, these functions can be expanded in terms of the hydrodynamic degrees of freedom, which are your chemical potential, temperature, and fluid velocity, etc., and their derivatives. Okay, so for example, I can write my curly E or script E as some equilibrium contribution epsilon plus corrections which are derivatives of the hydrodynamic variables. Okay, so these are called the constitutive relations for the system, and this is the basic postulate of hydrodynamics, that this derivative expansion exists. This derivative expansion near equilibrium makes a sense. That's the idea of hydrodynamics. What do these derivative corrections do? Well, these derivative corrections essentially capture departures from the state of thermal equilibrium. Let me give a heuristic argument that why this derivative expansion makes a sense. So as I said, we'll be interested in probing the system at length scales capital L, which are much larger than, say, the mean free path of the system, any microscopic scale associated to the system. Now, the mean free path or these microscopic length scales are inversely proportional to the temperature T. Okay. If I take inverse of this 1 by L, then it is essentially the derivative, the distance over which we are probing the system. So using this, I can say that derivative in units of temperature is much, much less than 1. So since this quantity is much, much less than 1, it makes sense to have an expansion in the number of derivatives, okay, where the successive terms in the expansion become smaller and smaller. Now, one has to be careful about the choice of hydrodynamic frame while writing the constitutive relations, which I showed earlier. So for example, when I'm expanding E as a function of epsilon plus derivative corrections, I have to make a frame choice. And this is because quantities such as the temperature or chemical potential or the fluid velocity are not uniquely defined out of equilibrium. These are by definition quantities which have a physical meaning in equilibrium, and out of equilibrium there's a freedom in redefining your temperature, chemical potential, etc. And one can use this freedom to choose a definition which can bring your constitutive relations to a relatively simpler form. I'll show an example soon. Before I move on, let me say that what are the dynamical equations of hydrodynamics? Well, the dynamical equations of hydrodynamics are pretty straightforward. These are nothing but the conservation equations for the conserved quantities of your system. So for the stress tensor, it's like del mu T mu nu equals 0, or for the current, it's like del mu J mu equals 0. Okay, so here I show you an example of a constitutive relation at first order in the derivative expansion. This is written in a frame which is called the Landau frame. So what is the Landau frame? In Landau frame, essentially I've chosen my temperature, chemical potential, and fluid velocity out of equilibrium such that I have fixed Q mu to be equal to 0. I have fixed E to be epsilon, the equilibrium value, and I've fixed the function capital N to be the charge density in equilibrium. Okay. Note that there are two scalar degrees worth of freedom in reparametrizing T and mu, which I have essentially used to fix capital E to epsilon and capital N to charge density N, the equilibrium value. And the one vector degree worth of freedom Q mu, I have essentially chosen in fixing, sorry, in U mu, I have essentially chosen to fix Q mu to be equal to 0. That being said, the constitutive relations look like these two first equations in this in the Landau frame. Okay, so there is some equilibrium contribution, which is epsilon u nu plus p delta mu nu, which is the perfect fluid contribution. And then there are corrections beyond the perfect fluid approximation, which are derivative corrections. For example, this term, which is proportional to the derivative of u, del alpha u alpha, and has a coefficient zeta, which is called the bulk viscosity. And similarly, this term, which is proportional to sigma alpha beta, the shear tensor defined here, also proportional to the derivatives of the velocity, one derivative term, and which has a coefficient eta, which is called the shear viscosity. And then there are higher derivative corrections. Similarly, in the current J mu, I have the equilibrium value n times u mu, where n is the equilibrium charge density. Then I have derivative corrections, and at first order, we have the electrical or charge conductivity sigma sitting over here. And then there are higher derivative corrections. Okay, so these coefficients zeta, eta, sigma, like the shear and bulk viscosities and the conductivity, are called the transport parameters of a system and quantify the response of the system to fluctuations which take it away from equilibrium. Okay, so this was a very quick introduction to hydrodynamics. I think everybody is very familiar with it, but if there are any questions, I'll be happy to answer anything, any confusion related to the notation I'm using or anything. Well, if there are no questions, let me move on to the second part of the talk. Sorry. Okay. So I'll now talk about thermal equilibrium and the hydrostatic generating functional. So before we delve further into hydrodynamic fluctuations around the state of thermal equilibrium, we would like to better understand the state of thermal equilibrium itself. Now, one very important property or aspect of thermal equilibrium is that we have thermal screening. So because of this screening, if I compute time-independent spatial correlation functions at distances which are larger than the correlation length of the system, then these correlation functions will fall off exponentially, right? So for example, if I consider some quantity O and I compute the 2-point function of O at x with O of 0, then it falls off exponentially as e to the minus x by L, where L is the correlation length of the system. Here I'm assuming that I'm away from any second order critical point or something, so that my correlation length L is actually a finite number, okay? Now, what I can do is that I can Fourier transform this expression from position space to momentum space. And the fact that these correlation functions fall off exponentially at larger distances than the correlation length in momentum space translates to the fact that if I look at zero frequency correlation of O at k with O at 0, in the limit vector k goes to 0, so small momentum limit, which is large wavelengths, long distances, and this is exactly what you want to probe in hydrodynamics, then in this limit, my correlation functions are functions of vector k squared. So they are analytic in k squared. Okay. In particular, there are no fractional powers of vector k squared. So there won't be a mod vector k cube or something like that, or log of mod vector k something. So the functions have to be analytic, and this is pretty easy to check by doing a Fourier transformation. So this is a pretty stringent criterion that comes from thermal equilibrium. Right now, I'm just mentioning it here, but as we'll move on in this talk, we'll realize that this is going to be a major player when I discuss the Schwinger-Keldysh effective field theory. Okay. Now, it turns out that the zero frequency correlation functions, which are the static or equilibrium correlation functions of conserved currents, can be obtained from an equilibrium generating functional W, which is a functional of the sources G mu nu and A mu. And by differentiating it with respect to these sources, I can compute my correlation functions. Okay, so this was shown in these two classic papers. Now, here the metric acts as the source for the stress energy tensor T mu nu, and the vector field A mu is the source for the current J mu. Okay. Now, in terms of this equilibrium generating functional, the 1-point functions for the stress tensor or the current are simply given by taking functional derivatives of W with the metric. So the 1-point function of T mu nu is essentially defined like this. It's one derivative of W with respect to the metric, functional derivative. And similarly, the functional derivative of W with respect to the vector field A mu gives me the current J mu. Okay. Higher point correlation functions can similarly be obtained by taking further derivatives with respect to the sources. So we have this static generating functional. Now, the hydrodynamic equations, which as I mentioned earlier, correspond to the conservation of the stress tensor T mu nu and the current J mu, can be satisfied by demanding the diffeomorphism and gauge invariance of this W. Okay, so when we are constructing this generating functional, we must demand diffeo and gauge invariance to ensure that my hydrodynamic equations automatically get satisfied. In particular, in the hydrodynamic regime, when the sources vary on length scales much larger than the correlation length of the system, things are varying on very long length scales, the generating functional admits a derivative expansion. Okay, so my W, I can write in a derivative expansion as integral over this measure of some del 0 terms which are independent of derivatives, then order del 1 terms which are one derivative terms, order del square terms, and so on. Here del m basically denotes terms which contain m derivatives and are made up of the sources G mu nu and A mu and the hydrodynamic variables such as the temperature, chemical potential, etc. Okay. So the problem of essentially constructing this generating functional boils down to constructing diffeomorphism and gauge invariant scalars, which you can insert at various orders in this derivative expansion. Basically, given your hydrodynamic variables mu t u mu, the chemical potential, temperature, and the fluid velocity, and the sources metric and the vector field mu, you have to construct at a particular given order in derivatives all possible scalar invariants that you can then put inside this generating functional with various coefficients that will sit in front of these terms, which are called the thermodynamic susceptibilities of your system. Okay. The constitutive relations for T mu nu and J mu that we discussed earlier will naturally follow in equilibrium when we vary this generating functional with respect to the sources. And in particular, the presence of a derivative expansion in this generating functional means that when I vary it with respect to the source to compute T mu nu or J mu, I will automatically imbibe, or I will automatically get a derivative expansion in T mu nu and J mu as well. Okay. So in equilibrium, the derivative expansion for the stress tensor and the current naturally follows from the derivative expansion that is inbuilt into this equilibrium generating functional. All right. Now let me give you a very simple example. Okay. For instance, suppose we are working to 0th order in derivatives. Now at this order, there are only two invariants essentially, the temperature T and the chemical potential mu. Thus, the generating functional to this order, to the 0th order, is essentially some function P of temperature T and the chemical potential mu. Okay. Now it turns out that this function P is nothing but the equilibrium pressure of the system. And it is easy to see that this is so because when I vary this generating functional with respect to the metric and the vector field A mu, I end up getting a stress tensor and a current which are of the perfect fluid form. Okay, so if I will end up getting T mu nu, which is epsilon plus P u mu plus P times G mu nu, and J mu is N u mu. So this has the perfect fluid form provided we identify the quantity minus P plus P del T plus mu del P del mu with epsilon, the equilibrium energy density, which is true. This is the Euler relation, and dP by d mu with the charge density N. Okay. So this is a very simple example where we work to the 0th order and vary the equilibrium generating functional, and out comes the equilibrium stress tensor and current, which have the perfect fluid form. Now, of course, one can go beyond this equilibrium approximation and starts including derivative corrections in the generating functional, okay, in the presence of sources. And then when you vary it with respect to the sources, we'll get corrections to the stress tensor and the current. Now, since investigating equilibrium properties is not going to be the focus of this talk, so I'm going to stop here as far as defining equilibrium and the properties of equilibrium are concerned. For higher orders in equilibrium, what happens when we go to even up to the second order in derivatives, those things are discussed here in these papers, which I've shown over here as an indicator, but I won't be discussing them. So this is where I'll stop my discussion of thermal equilibrium. And if there are any questions, I'll be happy to answer.
Sorry, I have a simple question.
Yes.
The information about the velocity field is in the effective action? Or you introduce it by saying that you are expanding the effective action around something?
Okay, so that is when you expand an effective action around something, but this particular generating functional is only an equilibrium construct. Okay, so I haven't shown it over here, but this generating functional is written in a particular frame, which is called the thermodynamic frame. So equilibrium can be quantified by having a time-lag killing vector in your system, okay? And you can define your fluid velocity in terms of this time-lag killing vector. So that information has gone on in constructing this generating functional. In particular, it's much more needed in higher orders, which I've not even shown here. But yeah, when you vary that with respect to the metric, etc., then this is what you get. And in particular, the thing that you're asking, expanding about a particular state and the fluctuations about that, I'm going to come to that soon. But right now, in this part of the talk, I was just talking about thermal equilibrium. So everything is time independent, and I'm working in an equilibrium setup. But very soon I'll move out of equilibrium.
Ashish.
Hi. Hi, Blaze.
Hi. Could you give us an example of a transport coefficient that would be non-trivial in the sense that you wouldn't get it just from thermodynamic considerations? Because what I have in mind is that typically take fluid hydrodynamics, compute the retarded Green's function, then take the omega to zero limit. Typically, at least if you limit yourself to first order ingredients, you would just get static susceptibilities that you could just, you know, predict to be there without going to any generating functional formalism. Right. Are there examples of higher order coefficients, or I'm sorry, I'm a bit unfamiliar with the static formalism. Other transport coefficients either at higher order ingredients or, I don't know, in the presence of parity breaking that you wouldn't be able to predict just as simply as thermodynamic static susceptibilities like dn over dt or dn over d mu. That would show up when you take the zero frequency limit of retarded Green's functions.
So I would say that, for example, again, I haven't shown here, but if you look at this generating functional and start constructing terms which are higher order in derivatives, then at first order in equilibrium, there's no term, but at second order, you find that there are 9 susceptibilities that will appear, which are new. So
Okay.
I'll point you to these papers actually that that appeared some time ago. And for example, at second order, you have susceptibilities that will depend upon the curvature of your manifold R, or on the acceleration squared or something of the fluid, or similar things. Like if you have background electric and magnetic fields, etc., they will depend on that as well. So
then if I took the zero frequency limit from the retarded Green's function at this order and gradient, I would retain some K dependence. It wouldn't just be something equal to the relevant static susceptibility.
Right. So, I mean, those are static susceptibilities, I would say, because, I mean, this is after all an equilibrium formulation, but they are not trivially some dn by d mu or dt by d mu or something. These are genuinely new terms that capture the response of your fluid to the presence of curvature, for example. Because there is a g mu, so they'll capture the response to curvature, etc. Are there other questions? Well, if not, I'll move to the next part of the talk. Okay, so far we have been discussing about, our discussion has been focused on the limit of thermal equilibrium. Let's not talk about fluctuations around the state of thermal equilibrium. Okay, so the equations of hydrodynamics are highly nonlinear in nature. This is what we should have in mind. So if you start with your equation del mu t mu nu equals 0 or del mu j mu equals 0, and as Jose was pointing out, if you start expanding it about a given equilibrium state and fluctuations about that particular state, then these equations are highly nonlinear. They will have interaction terms in particular between these fluctuations. Now, to gain some control over these complicated equations, as a first step, as a baby step, what one can do is that ignore these nonlinearities and work with the linearized theory. This approach has limited applicability because if you want to include the interactions between these fluctuating hydrodynamic degrees of freedom, then you cannot do, because you're by definition considering only the linearized version. What one actually needs is an approach which is based on an effective action. This approach based on an effective action can be used then to systematically take care of the interactions between the fluctuating degrees of freedom. So as I mentioned in the introduction to this talk, there are two major approaches which have an effective action approach towards studying fluctuating hydrodynamics. These are the stochastic hydrodynamics or the stochastic formalism first, and the Schwinger-Keldysh formalism, which has been formulated quite recently. Now, in the stochastic formalism, what one does is that one introduces random microscopic currents and stresses into the system to model the effects of the underlying thermal noise. Okay, and the correlation functions of the fluctuating degrees of freedom can then be obtained by integrating out this noise. So the stochastic approach is good. It gives you an effective action, but it has its limitations. For instance, the thermal noise is assumed to have correlations of a very specific type, as I'll point out quite soon, and these are put in by hand. It also does not allow for the most general interaction terms in the effective action. Okay, so the interaction terms that appear are quite restrictive in nature. Because of these two major shortcomings, it's not great. So what has been done more recently is to use the approach which is based on the Schwinger-Keldysh closed time path formalism to study non-equilibrium systems and formulate an EFT for fluctuating hydrodynamics. Okay. So what we'll do in the remaining of this talk is now discuss these two approaches in some detail and discuss the merits of the latter over the former. And to simplify the discussion and highlight the key points without loss of any generality, what I'll do is that I'll consider a conserved current J mu in the system and focus on the fluctuations of the associated conserved charge. Okay, so for now, I'll forget about the energy momentum sector of the theory. I'll just focus on the conserved current just to illustrate how things work. Okay. So, but first things first, I'll start with the linear response theory. This is going to be a super quick review, so no details here. Sorry for that. So this linear response theory is the most naive or pedestrian approach to computing these correlation functions, as it by definition ignores all non-linearities. So let me say that let me start with the equation for current conservation, which is del mu j mu equal to 0. Now, if I look at the linearized constitutive relations for this current j mu in the Landau frame, for example, then the time component is just the charge density n, and the spatial components are proportional to the derivatives of n. Okay. And if I insert this into del mu j mu equals 0, I end up getting the diffusion equation, which we all know and love, which is del t n minus d grad squared n equals 0, where t is the diffusion constant of your system. Now, what you can do is that you can solve this equation by Fourier transforming, okay, and compute a solution for n of omega comma vector k. That n omega k has, when you solve these equations, you'll find has something which requires n to be computed at t equals 0 comma k at momentum k. And I replace it with this quantity mu naught vector k by using this linear relation that my fluctuation n is actually proportional to a static susceptibility chi times my chemical potential mu, which is essentially sourcing this fluctuation. Okay, so this is one very basic tenet of linear response theory, that we assume that my fluctuation is directly proportional to the source with a constant with a proportionality constant, which is actually a constant. So this is something that is not going to be true when we study effective action constructions. There we will notice that the relation between n and mu is actually highly nonlinear. But in linear response theory, we assume by saying that this relation is linear and use it to solve the equation. So all said and done, this is what I obtained for my function n as a function of omega and k, and this is my result. It has a pole in the lower half plane. Now, the same thing can be computed in one other way by using quantum mechanical first order time dependent perturbation theory. So that part I have completely. Yeah, sure.
Can I ask you a question? It's Carl. Sorry, I don't have the video switched on right now. But couldn't I assume here, just use the equilibrium function of the susceptibility, chi? Then it's also a function of mu, right? And it would also be nonlinear.
Oh, you are saying to assume this chi to be a function. Of course, chi will depend upon your equilibrium susceptibility mu and t, and if those susceptibilities are fluctuating, then you can obtain a nonlinear relation between n and mu in here. But that's not the point of linear response theory. You are in principle right, but that is something that I'll discuss later. In linear response theory, you just assume that n is proportional to the chemical potential mu, and the constant of proportionality is the static susceptibility.
Yeah, okay, thank you.
You're welcome. All right, so the same quantity n can also be computed using first order time dependent perturbation theory, and there you get this n as an integral over the source mu convoluted with the retarded 2-point function of n, right, which acts like the Green's function. So that's another way of computing n, and in this approach what you do is that you equate the two values of n computed these two ways. One way is here, the other way is something I just spoke in words, and then compute the retarded 2-point function by comparing these two results for n. And in the end, all said and done, you end up with the retarded 2-point function of n in momentum space, which is d chi vector k squared by minus I omega plus d vector k squared. Okay, so this is the known, very celebrated retarded 2-point function, which has diffusive pole on the lower half plane at omega equals I minus id vector k squared. Just to be clear, this grnn is the retarded 2-point function, because if I write it in real time, it's actually proportional to a theta function, which makes sure that is non-zero only when t greater than t prime. Okay. Now, another quantity of interest that can be computed is the symmetric 2-point function, which is defined like this. And in Fourier space, it is given by this expression that it's 2t t chi vector k squared by omega squared plus dk squared whole squared. Now, in fact, the symmetric and retarded correlators are not independent of each other, but are related by the fluctuation dissipation theorem, which I've written over here. So the symmetric function is essentially related to the imaginary part of the retarded 2-point function. This was a super short summary of linear response theory. So what linear response theory does is that it provides us with the 2-point functions for fluctuating hydrodynamic variables. The most salient point to note here is that there are no interactions here. So these fluctuations n of omega comma k are like freely propagating modes. So if you are doing free quantum field, standard quantum field theory, then it will be like looking at the free part of the action. Okay, so this is what linear response theory is doing. Linearize the equations of motion, which are del mu j mu equal to 0, or if we were also including the energy momentum fluctuations, then del mu t mu nu equal to 0, and just solve these linearized equations using first order time dependent perturbation theory and compute your retarded and symmetric 2-point functions. Okay. Now comes the interesting part. The first approach that I want to discuss towards these effective action constructions, which is called the stochastic approach. So the stochastic approach to fluctuating hydrodynamics provides a way to include the non-linearities systematically via an effective action description. As I just said, this is somewhat an old approach. So these are some of the key early references in this direction. Now for simplicity, we'll continue working with the case for the diffusion of a single conserved charge to illustrate the procedure. Once again, I'm not going to look into energy momentum fluctuations. Now, what one does in the stochastic approach, interestingly, is that one augments the constitutive relations with a Gaussian random current, which has short range correlations. Okay. So recall that in the Landau frame, I showed this to you earlier as well. Let me just go back. In the Landau frame, if I'm looking at the constitutive relations for the current, then the spatial components are nothing but proportional to the derivatives of the charge density. Okay. What you do in the stochastic approach is you start with that, you say Ji is minus T times del IN, but you add a random current Ri to this purely by hand. Okay, this is a purely by hand construct, and assume that this random current Ri has only short distance Gaussian correlations. Okay, so my Ri Rj 2-point function is proportional to products of Kronecker and Dirac deltas, making sure it's only short ranged correlated. All right. So this Ri is purely put in by hand in the stochastic approach. Now with this Ri present, the equation of motion simply becomes del Tn minus d grad squared n equals theta, where theta is minus del I Ri. And this is following from the fact that my equation of motion is essentially del mu j mu equals 0. Del 0 j0 still gives me del Tn, but when I take del I ji, I have this minus d del In. But now since I've put in Ri by hand, this del I Ri will also enter. And I end up getting a Langevin type equation for the charge density fluctuations, which is dTn minus d grad squared n equals theta, where theta is minus del I Ri. Okay. And since Ri has been assumed to have short range Gaussian correlations, I can compute what the correlations in theta would look like. Okay, because theta is just del I Ri, and I'm getting theta 2-point function to be like this. This is also short range. Now, correlation functions in this approach in the stochastic formalism are defined as averages over the noise field theta. Okay, so we say that if we want to compute the correlation function of subquantities, then this is nothing but equal to the path integral over all possible realizations of this noise field theta, weighed in by some weight factor e to the minus w of theta. All right. And how does one determine this w of theta? Well, one says that I must choose a w of theta such that when I compute the theta 2-point function here, I must end up getting the 2-point function which I postulated theta must have, which I put in by hand. Okay, so it turns out that if I choose this quadratic w of theta, which has this form with the operator defined over here, d, if I choose w of theta to be this form and do this path integral, which will be a Gaussian path integral, I'll end up getting a theta 2-point function, which is shown over here. So this is the correct choice for the weight function for a Gaussian noise. Okay. Now, in general, we'll be interested, for example, in the case we are studying, what we'll actually be interested in is the correlation functions of the charge density n. And these are defined as, for example, if I'm looking at the 2-point function of n at tx with n at t prime x prime, then it is the path integral over the noise field theta, a path integral over n, the weight function e to the minus w theta, a delta function imposing the equation of motion, which is del Tn minus d grad squared n minus theta. Okay, and the 2 insertions of n. Okay, so this is essentially the quantity that we are interested in computing. Now what you can do is that you can take this delta function that imposes this equation of motion that I have dTn minus d grad squared n minus theta equals 0, and exponentiate it by introducing a new scalar variable rho. Okay, so I can write it as a path integral over rho e to the I times integral over rho times the equation of motion. Okay, So that way I can remove this delta function and I end up getting, in this equation, I end up removing this delta function. I end up inserting this path integral over rho with some e to the I integral EOM times rho, where EOM is essentially this quantity. Okay. Now, if you notice after this step that the integral over theta that is present over here becomes a Gaussian integral, and one can actually integrate out theta from this setup and end up getting the 2-point function of n to be given by dn d rho e to the minus s effective, which is a functional of n and rho times the 2 insertions of n. And what does the effective action look like? Well, this is how the effective action look like. It has a quadratic term, which is di rho squared, and a term which is linear in rho and multiplies the original equation of motion, dtn minus d grad squared n, okay, because theta has been integrated out. So this is how the effective action looks like once you, in this stochastic approach. And you can actually use this effective action to compute your 2-point functions, okay? So if you compute the n and 2-point function using this approach, the symmetric 2-point function, you get this result. And if you compute the retarded 2-point function, you get this result. And these, if you notice, are identical to the ones that we obtained using linear response theory, okay? So this is a triumph of the stochastic approach, that by using these short-ranged correlations by hand, putting in them by hand, and then describing my correlation functions to be path integral averages over these noise fields, I was able to reproduce the results of linear response theory. Okay, so this gives some credibility to this approach. However, with this effective action in hand, we can actually go beyond linear response now. And this is the biggest advantage, that we have an effective action and we can now systematically start going beyond the linear response theory. And how do we do that? Well, it's pretty straightforward to do it. What you can do is that we had the constitutive relation ji equals minus d del I n, but this was only to the linear order. What one can do is that start including non-linear terms. For example, I have included one term here, which is proportional to the product of n times pi I by w bar, where pi I are your momentum density fluctuations. Okay. And similarly, you can include higher non-linear terms like cubic, quartic, up to whatever order you are interested in working in the constitutive relation, and at the end, add this short range correlated noise field Ri. Once you have this constitutive relation, and we do exactly the same steps as before, integrate out the equation of motion. The equation of motion, by the way, will now be slightly more complicated, because when you compute del I ji, I will have a term which is minus d grad squared n, but I'll have terms that will come when del I acts on n pi I by w bar, or when del I acts on any other non-linearities that you're including, okay? So when you do that, in the end, the effective action that we'll get will be very similar. There will be a di rho squared term here. There will be a term which will be proportional to rho times the equation of motion. But the equation of motion, as I just said, will now be much more complicated. It will be dtn minus d grad squared n plus terms which will follow when del I acts on these non-linearities. So there will be a term like n times del I pi I by w bar and so on, sitting inside these braces, okay? And these are essentially your interaction terms. For example, this term n pi I by w bar, when di acts on it, will give a quadratic term inside these braces, and multiplied with rho, this is overall a cubic interaction term, okay? And if you have higher terms, higher non-linearities taken into account in your constitutive relations here, then you'll end up getting more complicated interaction terms in your effective action here, okay? So this is how in the stochastic approach, one constructs an effective action, which is to some extent ad hoc, but quite general at the same time. Okay, and one can compute the contributions of these non-linearities and, for example, compute loop corrections to your retarded or symmetric correlators. Okay. However, so as I said, the stochastic approach, though powerful, is somewhat limited because the interaction terms generated have at most 2 factors of the noise field rho. So this is something I just mentioned, that the effective action will have the form. The first term will stay the same. If you repeat this process, it's pretty easy to see. The first term will stay the same, di rho squared. The second term will have a linear term in rho times terms that will follow from the equation of motion. So they will have more complicated non-linearities proportional to n, pi I, etc. But as far as powers of rho are concerned, it's pretty restrictive. The noise field either enters quadratically and through a very specific term here, or it is linear and multiplies with other terms in the effective action. But
can I ask?
Yeah, sure.
The covariance of the noise, this capital C.
Right.
is what determines the chi in the Green's functions.
Yeah, so this is the point. Yeah, thanks for bringing it out. I forgot it. So I must have mentioned that when I used this stochastic approach to compute my symmetric and retarded correlators, to start with, when I had to fix the strength of this noise, I had this arbitrary constant C sitting over here. But when I computed my retarded and symmetric correlators, I'll get some result which will have C sitting over here. But then I want to match it with the linear response results as well. So that fixes my strength of the noise C in terms of the susceptibility and the diffusion constant, etc.
Okay.
Yeah. Okay.
Sorry, can I ask a question?
Yeah, sure.
My question is about the previous question. In fact, you fixed C, I think, by using the relation between GRNN and GSMN, which is actually the fluctuation dissipation theorem. Then my question is how to do that in nonlinear regime. In linear regime, I can understand, but in nonlinear regime, how to fix C when including n pi I over W bar term, for example, in JI current? Is it the same?
Well, as far as the stochastic approach is concerned, it is the same, because in the stochastic approach at the tree level, you want things to match with linear response theory, and that is what will fix C for you. Then whatever sits in coefficients of n pi I by WR is whatever comes from the constitutive relations. Okay. For example, if your term in the constitutive relations, which is proportional to the shear viscosity, then if that term is included in the in the frame you are working in, for example, here I'm working in the Landau frame, then the coefficient here that sits is shear viscosity or something. Okay, I mean, these will essentially come down from the constitutive relations you have in the particular hydrodynamic frame you are working in.
Okay, thanks.
Am I clear? So the C essentially was fixed by demanding, as you said, fluctuation dissipation theorem, or saying that the results that I obtained at the tree level, I'm calling it tree level because this action is essentially quadratic, right? So just this quadratic action should be able to reproduce my linear response theory results. That just fixed C for me, and anything beyond that will essentially come from whatever constitutive relations you have. So if your constitutive relations have some transport parameters sitting in them, then when I study fluctuations about a given equilibrium state, that is what will sit over here. And that's it. That will end up eventually in the correlation functions as well.
Okay, thanks. Thanks.
Okay, so I was pointing out the limitations of the stochastic approach, that this approach is powerful. It provides me an effective action and a systematic way to introduce non-linearities to compute non-linear contributions to correlation functions. But there are at most two factors of the noise field rho, for example. And this limitation is a consequence, of course, of the initial assumption that the underlying noise has short-range Gaussian correlations, because we put in a noise of a very specific kind right in the beginning. I ended up getting an effective action, which also was quite restrictive. The approach also looks very phenomenological, which relies on somewhat ad hoc motivations that you just put in the noise field by hand. Okay. So more recently, people have formulated a Schwinger-Keldysh effective action based approach, which is based on symmetry principles and is valid even far away from equilibrium. And these are some of the main references where this approach was first developed. So I'll now discuss the Schwinger-Keldysh approach in some detail. But before that, are there any questions, other questions?
Yeah, I have a question. Why would you like to have higher order terms in this rho field?
Yeah, okay, this is a nice question. I mean, in principle, the Gaussian approximation is a good approximation, and there's nothing, I mean, yeah, assuming that the noise field is Gaussian is fine. But in principle, it is possible for this noise field to be non-Gaussian, right? And if that is the case, then this simple structure of the effective action won't work out. So this simple structure is actually a consequence of assuming Gaussian short-range nature for the noise field, which is fine, but it may not always be true. So it will be better to have an effective action which is more general than this as well.
Okay, I see. But I could, for example, when you write here the delta function or the equation motion, I could just add some terms which are, in the exponent on the right-hand side. Couldn't I just add some polynomials in rho to the n, or rho squared, or rho to the 3, or rho to the 4?
Well, I mean, this particular step is very specific. So what I'm doing here is exponentiating that equation of motion. And if I want to do that, then the only thing that can appear is just rho times the equation of motion. I cannot add arbitrary terms here.
Okay, okay.
Because then this exponentiation won't work.
Yeah. Okay.
Okay, so let me now move on to the last part of the talk, which is somewhat the most interesting as well. So let me now talk about the Schwinger-Keldysh approach to fluctuating hydrodynamics. And once again, for simplicity, I'll focus on the case of the diffusion of a conserved current J mu. I'll forget about this energy momentum sector for the time being. Now, in the Schwinger-Keldysh approach, what one does is that one works with the generating functional, which is a generalization of the static generating functional we talked about in the second part of this talk. This generating functional is defined on a closed time path, and we have to take two copies of my degrees of freedom and as well as the sources. Okay, so I have tried to illustrate it here in this diagram, that I have some density matrix rho naught at time ti equals minus infinity, the initial time. The closed time path that I consider in the Schwinger-Keldysh formalism first goes forward in time all the way to infinity and then comes back to minus infinity. If I'm interested in computing the correlation functions of some operator O, then I have to first consider two copies of this. So the first copy, I mean the subscript 1 is inserted on the upper leg of the CTP contour, closed time path, and the subscript 2 are things that are inserted on the lower leg. Okay, so if I have to consider the correlation functions of O, I'll have to take two copies of O. One copy I have to insert on the upper leg and the other copy on the lower leg. Okay, and similarly, if this O is being sourced by in some field phi, then I have to consider two copies of phi as well. Okay, so this is a peculiarity of this formalism, and it's not very intuitive when you first look at it. So what happens is that if you want to compute the correlation functions of some operator O, then you work with a Schwinger-Keldysh generating functional, which I have written over here. It's e to the power w of phi1, phi2, where phi is the source for O, but I had to take two copies of it, phi1 on the upper leg, phi2 on the lower leg. And this generating functional is defined as a trace over rho naught. Rho naught is my density matrix, times path ordered integral e to the I dt of O1 phi1 minus O2 phi2. So this form makes it clear that phi1 sources the first copy O1 and phi2 sources the second copy O2. And this relative minus sign is because the time is running in the reverse direction on the second half of the contour. And the path ordering is essentially a very fancy way to say that things that are inserted on the upper leg of the contour are time ordered and things on the lower leg are anti-time ordered. Okay, we won't rely too much on this explicit picture or something. So even if it's not very clear, it's fine. Now, what I've done here is that I've written this Schwinger-Keldysh generating functional W in a basis, which is the 1-2 basis. But what I can do is that I can change basis and write it in a basis, which is called the Keldysh basis, also called the RA basis. Okay. In this basis, I defined my operator OR as the average of the two copies, O1 plus O2 over 2, and OA as the difference of the two copies, O1 minus O2. Similarly, I define my source phi R as two copies, phi1 plus phi2 by 2, the average of the two copies, and phi A as the difference of the two copies, phi1 minus phi2. So if I work in this basis, it's pretty straightforward to see that my Schwinger-Keldysh effective generating functional, looks like e to the w of phi R phi A now as trace over rho naught path ordered e to the OR times phi A plus OA times phi R. Okay, it's a one-line step to go from here to here if I change this basis from 1, 2 to the RA basis. And now it's clear in RA basis that phi A is the thing that acts as the source for OR and phi R is the thing that acts as source for OA. All right. Now, what are the correlation functions in the Keldysh basis? Well, to compute correlation functions in the Keldysh basis, what we do is that we take derivatives of this generating functional with respect to the appropriate sources, as one would expect one to do. So for example, if I want to compute the correlation function at time t1, t2 between operator insertions alpha 1, alpha 2. Okay, so note here this alpha 1, alpha 2 are my A or R indices. Okay, so for example, if I insert RR, it means I am computing OR at T1, OR at T2. All right. So this is a very general notation. So alpha 1, alpha 2 can be AA, RR, AR or RA. Okay, and they are all defined with respect to the derivatives of the generating functional. So two derivatives of the generating functional with respect to the corresponding sources. All right. Now one has to just be careful that when I have to take compute correlation functions of OR, I have to take derivatives with respect to phi A, the conjugate quantity. That's why when I had to compute alpha 1 and alpha 2, I took derivatives with respect to phi alpha 1 bar and alpha 2 bar, where if alpha is A and R, alpha bar is R and A. Okay, once again, this structure is because the source for OR is actually phi A and the source for OA is actually phi R. Okay, so it's pretty straightforward exercise to do. Okay, so but the question, one may ask the question that what's the advantage of working in this Keldysh basis as opposed to the 1-2 basis that we originally started with? Well, there is a very distinct advantage, and the advantage is this, that if we want to compute the retarded 2-point function of the operator O, which we would like to, or the advanced 2-point function or the symmetric 2-point function in the standard single copy formalism, then in the Schwinger-Keldysh formalism, they just map directly to the RA, AR or RR type 2-point functions. Okay, so for example, if you want to compute the retarded correlators of O at x1 at x and O at x2, then it's nothing but the RA type correlator of O at x1, O at x2. Okay, so if you compute OR at x1, OA at x2, it will give you OX1, OX2 retarded correlator in the single copy formalism. Okay, I'm not giving proofs of these things here, but you have to take it from me that this is the advantage of this formalism, and in particular working in the Keldysh basis, RA basis, that you compute these RA kind correlators and they directly map to your single copy retarded advanced or symmetric correlators. Okay. Now, to construct this generating functional, we have to keep certain things in mind and certain conditions that it satisfies. And I've written down 3 conditions here. The first one of them is that if I set my sources to be identical, so if I set phi 1 equal to phi 2, the two sources on the two legs of the contour to be same, then my generating functional vanishes. Or equivalently, if I set the difference field phi A, which was basically phi 1 minus phi 2 to be equal to 0, then for arbitrary choices of phi R, my W is still equal to 0. Okay, it's this, both these statements are the same, one written in the 1-2 basis, and here it's expressed in the AR or RA basis. Okay, and it simply follows from the representation of this generating functional as a trace over U, where U is the time evolution operator in the presence of sources phi 1 times the density matrix rho naught times U dagger, okay, in the presence of the sources phi 2. So this particular representation of this generating functional, if we use, deriving these properties pretty straightforward. Similarly, I can also talk about the complex conjugation property of this generating functional, and it turns out that W star of phi 1 and phi 2 should be equal to W of phi 2, phi 1, okay? And the real part of W should be less than equal to 0. All of these properties can be derived from this representation, which I'm not going to do. I'm just going to state that. Now, those 3 properties are standard, fine, but there's one additional property which is quite interesting, and it's called the KMS property. So if my density matrix rho naught that I had at T equals minus infinity is actually a thermal density matrix, so it has the form e to the minus beta h upon trace e to the minus beta h, then my Schwinger-Keldysh generating functional will satisfy an additional condition, which is called the KMS condition. And once again, deriving this is pretty straightforward. What it amounts to is saying that my W of phi 1 comma phi 2 should be equal to W of phi 1 tilde and phi 2 tilde, where phi 1 tilde is some operator theta acting on phi 1 and phi 2 tilde is the same operator theta acting on phi 2, where T has now been translated along the thermal circle by an amount beta, so T to T plus I beta, okay? And what is this operator theta? These theta are any discrete symmetries the system may have. For example, theta is the time reversal operator T combined with other discrete symmetries of the system, such as charge conjugation or parity, etc. So this is a pretty straightforward property that also follows from the representation of the generating functional, but it plays a very key role when I discuss about analyticity of the retarded correlators soon. Here I have shown a very simple example that if my discrete operator is parity times time reversal, then how will my fields look like? So phi1 tilde, my source will be phi1 of minus t minus x trivially, and phi2 tilde will be phi2 of minus t minus I beta comma minus x. So in KMS, this translation along the thermal circle is very important. All it does is that it imposes that W of phi1 phi2 should be equal to W of phi1 tilde phi2 tilde. This KMS constraint will play a crucial role in ensuring the retarded correlators, that the retarded correlators which are computed using this Schwinger-Keldysh approach become analytic and k-squared in the static limit. Okay, so this point I will elaborate upon pretty soon. But let me first talk about the effective action. So just as in any effective theory, we assume that the UV degrees of freedom associated to the system can be integrated out. And if we do so, we end up writing Schwinger-Keldysh generating functional in terms of an effective action, which depends upon my sources phi and some IR degrees of freedom, which I collectively denote by chi. Okay, so I say that e to the W of phi1 phi2 should be equal to the path integral over these IR degrees of freedom, and I have to take 2 copies of these variables as well. So d chi1 d chi2 for the 2 arms of the contour, e to the is effective, which is a functional of my degrees of freedom chi1 and chi2, the infrared degrees of freedom, and my sources phi1 and phi2, and there is a cutoff epsilon. Okay, and the boundary conditions that I impose are that at time tf, which is the extreme right end of the closed time path contour, chi1 of tf should be equal to chi2 of tf, and this is used to impose the trace that was present in the generating functional. Okay, so this is how my generating functional can be expressed in terms of an effective action, which is the Schwinger-Keldysh effective action. Now, if you recall, I just a couple of slides ago showed a few constraints that are satisfied by this generating functional, which follow from its representation as trace u rho naught u dagger, okay, over the closed time path. I can just straightforward take these constraints on W and find what they correspond to as far as this effective action is concerned. Okay, and if I do that, what I find is that the effective action, if I set all my A-type fields to be equal to 0, must be equal to 0. Similarly, under complex conjugation, S star effective must behave like this. Okay, the imaginary part of S effective should be greater than or equal to 0. If my initial density matrix rho naught was a thermal density matrix, then W satisfied this constraint that W of phi1 phi2 should be W of phi1 tilde phi2 tilde. So this KMS symmetry should also be imposed on the effective action. And finally, if there is any other symmetry of the action S naught that is preserved by the state rho naught, that should also be imposed. Okay, so these are the general principles that are used to construct the Schwinger-Keldysh effective action. So this was a general summary that I wanted to give of the Schwinger-Keldysh approach before we jump into our example of interest, which is the construction of this effective field theory for the diffusion of a single conserved current G mu. So are there any questions?
So I have a question. So all these properties of that you presented are very kinematical, very structural in general, right, except KMS, which says that you are perturbing around the standard equilibrium.
Right.
But you didn't say anything about what the form of the effective action is.
Okay.
For example, is it local?
Yeah, so what I'm going to do is now is that I want to actually compute this effective action for the particular case that we have in mind. So that way it will be easier to illustrate. Right now, I just gave the general principles, and as you very rightly pointed out, mostly the kinematic constraints that the generating functional or the effective action must satisfy along with the KMS condition. So let's now actually look at the case of interest, which is the diffusion of a single conserved current J mu. So as we discussed, we'll need to have 2 copies of the sources of J mu. So the source for J mu was a vector field A mu, so I'll have to have 2 copies of it, A1 mu and A2 mu, or equivalently, if I work in the RA basis, I'll have 2 copies AR mu and AA mu. We'll also have 2 copies of the correct IR degrees of freedom, okay, which I originally denoted by chi, but right now I'm denoting them by this var phi notation, so phi R and phi A. And apart from the kinematic Schwinger-Keldysh constraints that I outlined in the previous part of the talk, this action must also satisfy something additional. For instance, it should be invariant under the gauge transformations of these 2 fields A1 mu and A2 mu. Okay. Also, the equations of motion that must follow from the variation of this effective action must imply the conservation of these two copies of the current. So del mu j mu 1 and del mu j mu 2 equals 0. Both should be satisfied. And finally, if I'm working in the ordinary fluid phase as opposed to a superfluid phase, then I must also have a shift symmetry for the field phi r. Phi r must be invariant under the shift phi r to phi r plus lambda of vector x, or equivalently, the action should only depend upon the time derivatives of phi r, phi dot r. Okay. So these are the additional things that I have to put in. Okay. And sorry. And once I do all that, put all the kinematic constraints and these additional constraints that the Schwinger-Keldysh effective action must meet, I end up constructing an effective action which looks like this. Okay, so this has a pretty horrific form. I have decomposed it into 4 parts. The first part is essentially the free part. Okay, it's only quadratic terms. Phi a times dtn minus sigma over chi grad square delta n, etc. Then I have 3-point interaction terms between, and in particular, I have truncated this effective action at cubic order in interactions. Okay, so it's not that there are only cubic interactions. There are, of course, higher non-linearities that are present, as are always there in hydrodynamics. But for the sake of illustration, I've just truncated it at the cubic order and second order in derivatives. Okay. So in the 3-point part, I have 2 interaction terms between the charge density fluctuation delta n and my noise field phi a, the associated conjugate field phi a. Similarly, I have 2-point interaction terms which depend upon the sources, the 2 copies of the sources, AA and AR, and the time component in particular. And then I have 3-point couplings that involve the couplings with the sources. Okay. So this is the structure of the effective action. Now, there's one very important thing that has gone in construction, in the construction of this effective action, and it's that while constructing it, we did not impose the KMS condition. Okay, so we took into account all the kinematic constraints that are provided by the Schwinger-Keldysh construction itself and the additional cage invariance constraints, etc. But we did not put in the KMS constraint. Now, the KMS constraint at the level of this effective action, what it does is that it basically says that my strength sigma tilde here, my strength of this quadratic term in noise here, is actually equal to the sigma, the conductivity that sits over here. Okay, so if I had imposed the KMS condition, I would have set sigma tilde equal to sigma, but I deliberately did not impose that condition and imposed all other constraints to construct this action. Okay. Now we will see why. But before, let me just mention that at the tree level, the Schwinger-Keldysh effective action reproduces the correct retarded and symmetric 2-point functions. Okay, so if I use the tree level, that just the 2-point part of this effective action, then I end up getting the correct 2-point functions, the retarded and the symmetric, for the charge density fluctuations, as in linear response theory or the stochastic approach. With the cubic couplings now put in, we can compute the 1 loop corrections to the retarded 2-point function. So this is what we did. We constructed the loop contributions. Sorry, we computed the loop contributions to the charge density retarded 2-point function GRNN, as I was saying earlier. These are the 4 loops that contributed to it. And in computing these loops, the propagators that I'm using for, say, for example, delta n phi a or phi a delta n, etc., I could compute them from the free part of this theory. Okay, so this part is standard. I can compute these propagators from the free part of the theory, and then using the cubic interaction vertices that I have, I can construct the contributions that will go in to the retarded 2-point function, and these are the 4 loops that contribute. Okay, so if I do this loop computations, I end up getting a result for the 1 loop corrections to the retarded 2-point function in diffusion. And this is how the results look like. Okay, it has a pretty complicated form. Not the exact form is not important. What is important is to note that this function I1 of p that sits over here has a root of vector k squared in it. So it's very non-analytic in nature. Okay. But if you recall, in the second part of this talk I was discussing, I mentioned that because of thermal screening in equilibrium, I would expect that when I take the limit of equilibrium of this 1 loop correction to the 2-point function, if I take the equilibrium limit, I must end up with something which is purely analytic in nature. Okay, so to do that, to do the equilibrium limit, I set omega equal to 0, and I get the 1 loop correction which looks like this. Okay, very interestingly, it still continues to be non-analytic, so it has a mod vector k cube dependence, But notice, okay, so notice that if I set the KMS constraint, which I mentioned basically amounts to saying that sigma tilde, the strength of my noise fluctuations, is actually equal to the conductivity sigma. If I impose the KMS condition, then this quantity sigma tilde over sigma just becomes 1 and its derivative vanishes. And in that limit, my one loop correction becomes analytic. Okay. So this is the key point that I wanted to highlight, is that as soon as the KMS condition is imposed, which amounts to saying that sigma tilde equal to sigma, the non-analytic corrections in the static limit vanish. Okay. So these computations essentially tie in the two parts of this talk quite neatly. In the second part, we were discussing about the equilibrium generating functional and the constraint of analyticity that comes from thermal screening. Here we see that in this very general Schwinger-Keldysh effective field theory construction, this analyticity is actually being brought about the KMS condition. So if I don't impose the KMS condition, I don't end up getting analytic results. So yeah.
So sorry, Ashish, can I ask you something?
Yeah, sure.
What about the non-analyticity in omega? What if you don't set omega to 0? That's the usual non-analyticity that people talk about.
Yeah. So that's the usual long-term tails, as I would say, right? People take the k goes to 0 limit and talk about the non-analyticity in omega, but we were interested in the other limit because we wanted to relate to the static generating functional and the analyticity in the static limit. So we took the limit where we set omega to 0 and looked at the momentum space analyticity.
But so is there non-analyticity in omega still, or are you claiming that that's also gone?
No, I mean, here I have taken omega equals 0. So there is no point in asking whether there is a non-analyticity in omega. But in general, if omega is finite, there are non-analytic contributions. Okay. Away from equilibrium, there are always, and these are these long time tails, right? Because the non-analytic,
right, exactly.
Yeah, so non-analyticities and omega will persist, and these are the long time tails. And yeah, but specifically the omega goes to 0 limit, which is the equilibrium limit. There I expect things to be analytic in k squared, and it turns out to be true if and only if I impose the KMS condition.
But you could have imposed the KMS condition at the effective action. Is this not, this doesn't commute somehow? I mean, because normally people just impose it on the effective action and then they don't worry about sigma tilde and sigma.
Exactly.
And there's nothing to discuss then.
So the way we approached this problem was this. We saw these computations, we did these computations, and there are other papers as well. And we saw that these results in the static limit were analytic, but it was not clear that what is actually bringing about this analyticity. What is going in that is doing that. And to unwind it, what we did was, in constructing the effective action, let go some of these constraints. Okay, and if you let go the KMS constraint in the constructing the effective action, it turns out that you realize that it's this piece that is actually bringing about the analyticity. If you impose it right at the level of the action and then do the computations, you get nice analytic results, but you never know what went in, how exactly this was being brought about.
I see. Okay. So, I mean, there was maybe 2-3 years ago, there was a paper by Sean Hartnell and Luca Della Creta, right? Which I think they do the same calculation. They compute the effective action for diffusion and they look at long time tails and this non-analyticity. So do you have the same result as they do?
Exactly. So one of our motivations was their paper actually, and we looked at their paper and we saw that in the static limit, things seem to be analytic, but how exactly it is being brought about, we didn't know. So we just basically reproduced the calculations, but now deriving the effective action without the KMS condition put in. So slightly more general than that what they did. And then without imposing these KMS, did this loop corrections and everything. And in the end, only we imposed this KMS condition.
Okay. I think now I understand. Okay, thanks a lot.
Yeah. All right, so we didn't stop here at this level of computing corrections, loop corrections in the case of charge diffusion. What we decided to do was to be doubly sure and work with the full theory of relativistic hydrodynamics. So basically include energy momentum fluctuations as well. Okay, so to do that, I have introduced some notation here, which won't be very important, but just to say, I now have the fluid velocity u mu normalized in units of the temperature T, which I call the vector beta mu, and I'll study fluctuations in this vector as well. But what we did was we took a limiting case of this full relativistic hydrodynamics, and this limiting case was obtained by imposing the condition that I'm going to ignore or set my fluctuations in the time component of beta to be 0 and delta beta I to be 0, and correspondingly to so XA mu is the noise partner associated with this field beta mu, and I will set XAT to 0 and DIXIA to 0. Okay, so this is diffusion with energy momentum fluctuations, but a very specific subsector of it, which we dubbed diffusive hydrodynamics. Okay, so this is not full hydrodynamics because physically speaking, this limit amounts to ignoring the fluctuations in the energy density and working only with diffusive and shear modes of the system. Okay, so this was only a simplifying step. Now, even with this simplification put in, when we have ignored the sound modes or the energy density fluctuations in the system, and in longitudinal modes considered only diffusive and shear modes, still the action is still quite complicated. So this is how the Schwinger-Keldysh effective action looks if I work in this subsector called diffusive hydrodynamics. The black terms are the ones that were present early on in my Schwinger-Keldysh, earlier in my Schwinger-Keldysh effective action, and the orange terms are the new terms that come in because I am now putting in momentum fluctuations as well. Okay. So as you can see, the action now becomes quite ghastly and it has lots of new interaction terms and everything. We do the same thing with this new set of interaction terms and new set of propagators corresponding to momentum fluctuations and its corresponding noise partner X mu A, which can be computed from this tree level action. Okay, this tree level action now has quadratic terms in pi I and xia, and this can be used to compute these propagators or 2-point functions for pi I and xia as well. So with the previous as well as this new set of interactions and propagators in hand now, what we did was we computed the loop corrections to the retarded 2-point function. And these are the new 7 diagrams that come into play. Okay, so previously we had 4 diagrams and now we have 7 more diagrams that contribute to the 2-point function, the retarded 2-point function, and we computed their contribution. Once again, just let me tell you that to understand the role of KMS better, what we did was in constructing this effective action, we did not impose the KMS condition. We imposed all other requirements, but not the KMS condition. And at the level of this action, KMS corresponds to setting sigma tilde equals sigma and eta tilde that sits here to the shear viscosity equal to the shear viscosity eta. Okay, so we did not impose the KMS condition and we computed our loop corrections. The result for the one loop corrections that came out from these set of diagrams is quite complicated, so I'm not going to show that. What I'm going to show is just the omega equals 0 limit of that correction. So all said and done, my retarded 2-point function, one loop corrections to it in this sector of subsector of hydrodynamics, which we dub diffusive hydrodynamics, where we have basically integrated out the sound modes working only with the shear and diffusive modes. In this sector, I find that the one loop correction looks like this. Okay, here these functions I0, I1, J2 and J4 are all non-analytic functions of K in the limit where frequency has been set to 0, the static limit. And you can see that there are certain coefficients that sit in front of these non-analytic terms. Very interestingly, once again, as soon as I impose the KMS condition, eta tilde equals eta and sigma tilde equals sigma, these coefficients all vanish and therefore all non-analytic contributions to the 2-point function in the static limit go away. Okay. So once again, the KMS condition is ensuring analyticity in the static limit. As soon as we impose the KMS condition, the non-analytic one loop corrections above vanish. These constructions highlight the crucial role that is played by the KMS condition in ensuring the consistency of the Schwinger-Keldysh EFT formalism. Before these calculations, it was not clear what is bringing about this analyticity and how is this inbuilt, but these calculations explicitly show that it's the KMS condition. If it is not imposed, then the relation between the static generating functional, which is a story I discussed in the second part of the talk, and the Schwinger-Keldysh generating functional, this relation is somewhat flawed. Okay. Now one can also compute the symmetric correlators in these models, which we did in the paper, but I didn't have the time to show them here. And interestingly, these symmetric correlators continue to be non-analytic even in the limit omega goes to 0. even after imposing the KMS condition. But that's not a problem for us because the physical causal response of a system to external perturbations is captured by a retarded correlator, not by a symmetric correlator. The symmetric correlator does not have a physical meaning as opposed to the retarded correlator, which captures the causal response. So there the analyticity is very important, whereas the symmetric correlator staying non-analytic even in the static limit after imposing KMS is not a worry. So I'll now just summarize the talk. So in this talk, we started by reviewing the basic ideas of hydrodynamics. We then discussed the state of thermal equilibrium in a system and the equilibrium generating functional, which gave rise to the equilibrium correlation functions of the stress energy tensor and other conserved currents in the system. We then investigated two approaches to study fluctuations out of equilibrium. These were the stochastic approach, which is the somewhat older and more restrictive approach, and the Schwinger-Keldysh approach, which is the more recent one and the more powerful of the two. And we also discussed the merits of the latter over the former. Finally, we discussed in some detail in the Schwinger-Keldysh effective field theory construction of diffusive hydrodynamics, which was a subsector of hydrodynamics where we were studying the diffusive and shear fluctuations, but integrated out the sound modes just to simplify the computations. We argued that the analyticity of the retarded correlator in the static limit, omega goes to 0 limit, is a consequence of the KMS symmetry that is inbuilt in the Schwinger-Keldysh formalism. Now, in the future, it would be interesting to study the analyticity properties in the full Schwinger-Keldysh EFT and not just the diffusive hydrodynamic sector. Okay, so not integrating out the sound modes, taking them also into account. However, the action will be even more ghastly, but yeah, it would be interesting to study how the loop corrections work out there and how, and indeed KMS ensures analyticity in the full relativistic hydrodynamics formalism and not just a subsector of it. We are also able to check the analyticity properties at one loop level in all these computations that I was showing. It would be interesting to find out whether one can derive these at a fully non-perturbative level. So something at the level of action itself, if something at the level of action itself tells me that when I take the static limit of the correlation functions computed from this effective action, I end up getting something which is analytic, that would be great because then we won't have to check it loop by loop. One can also compute the non-analytic behavior at finite omega, which is something Sasha pointed out, which are called the long time tails. And these signify the breakdown of the derivative expansion at very long times due to the cumulative buildup of the effects of these thermal fluctuations. So this is a work in progress where we are studying these long time tails in diffusive hydrodynamics, okay, which are non-analyticities in omega rather than K. So I'll thank you for your attention now. And if there are any questions, I'll be happy to answer.
Okay, so thank you very much, Ashish. That was very nice. Are there questions, more questions or comments?
I have a question.
Yeah.
Ashish, thank you for your very nice talk. Could you please show the slide in which you showed the Feynman diagrams associated with your work? Oh, very good. Okay. What are the dashed lines here?
I'm very sorry. I should have explained it. I should have said that. Okay. So when I was just looking at the pure diffusive sector, no energy momentum fluctuations included. So my solid lines are fluctuations in the charge density, and my wavy lines are my associated noise partner phi A, and the dashed dotted line is essentially the background field A. And when I go to the energy momentum sector as well, then my bold solid lines are the momentum fluctuations pi I, and these coiled lines are associated noise partners x mu, capital X mu.
And then why do we have some external legs which are not, which are neither the N field nor the noise field?
Oh, that's a good question. These you're talking about these background fields?
Yes, yes, exactly. Second line, yes, yes.
So when you vary the effective action, so this will require me to have a pen and paper, but when you vary the effective action to compute these AR or RA type correlators, you will have contributions which look like 3-point functions, like an N phi A, but the two phi A momenta are contracted. So it's like N and going to a phi A loop, and they are contracted. So it's basically, and those essentially follow from cubic couplings with the gauge fields that I've shown over here. Okay. So I didn't go into the details of the computation itself, but if you carry out the computation, these cubic couplings with the gauge field will bring on such diagrams. Okay, and this is what I've shown over here. So it's basically like a coiled XA contracting with a delta N fluctuation and a background field. And this coupling is actually coming from these kind of background couplings. Yeah.
Okay, thanks. And sorry, I have also one more question. This is a technical question. When you compute your loops, what is the upper bound of your integrals? I mean, how do you regularize your integrals?
Right. Thanks for asking. So what we did was just use a cutoff regular a UV cutoff in our integrals, and in these results, I have not showed the results that I showed here. For example, here I did not include any cutoff dependent terms. So this is just the cutoff independent contribution, and this is what we're talking about. But we used a UV cutoff when we were doing the integrals.
Oh yeah. Thanks. Thank you.
Can I ask a question as well? Can you hear me?
Yeah, I can hear you.
Okay, good. Sorry. Yeah, I would like to ask, you mentioned that now the symmetric Green's function was not analytic anymore in the static limit, but I thought that when you're just in thermodynamics and you calculate, there's only one Green's function basically, and you can take the retarded one and then get all others by just taking imaginary part and certain combinations of real and imaginary. But now that does not seem to be true anymore in your formalism. Is that right?
Well, what you're saying is that if I can compute one of them, I can compute the others. Is essentially this statement of this KMS condition or the fluctuation dissipation theorem.
Exactly. Yeah.
The imaginary part of the retarded correlator will give you the symmetric correlator, etc. But that's only, I think, at the tree level. Once you include all these corrections, once you take all of them into account, it turns out that the symmetric correlators are indeed non-analytic. So they have non-analytic terms, but we are not bothered by them simply because of the fact that these symmetric correlators are not carrying any physical response to an external perturbation. The causal physical response is actually being captured by the retarded correlators, and that is where this analyticity must have come about, which it comes about if you impose KMS.
Okay.
Yeah. So basically, what I want to say is that computing the retarded symmetric correlator from the retarded correlator, etc., those are the tree level things. Once you include all these loop corrections, etc., those results will also start getting modified.
Yeah, but not to get confused. I thought that this relation, say from quantum field theory perspective, right? If I would integrate out all the quantum fluctuations as opposed to what you're doing, which are the statistical fluctuations, and after integrating out the quantum fluctuation, I would still have this relation, right? It's only upon including also the statistical, do I understand this correctly? That the symmetric is not simply anymore the imaginary part of the retarded. Because, in ADS-CFT, for example, we do, we have fully interacting quantum field theory, right? And the only thing which we don't have are statistical fluctuations because they are suppressed like 1 over n. And we know that these relations hold in the ADS-CFT correspondence, right? We can calculate retarded, advanced, and symmetric, and I guess who was his son and Herzog, they showed how to do Schwinger-Keldysh correlators, and all of these relations work for the non-perturbative, for the ADS-CFT Green's functions on the Schwinger-Keldysh contour. And they are supposed to include all, quantum corrections, but they don't have the statistical. Do I see this? Do I understand this correctly?
So one thing that I also try to point about is that I think you are talking about this relation. Yeah, something like this, right?
I understand this is what you say is not true anymore.
Right.
Because of... the left-hand side would have non-analyticities in the static limit, right?
Right. The left-hand side actually has non-analyticities, but actually if you look at this relation, this relation is valid only in the hydrodynamic limit. So in the limit where omega is very, very small. So I start with a retarded 2-point function, okay? And I can take its imaginary part and make a series expansion in small omega. And this relation, all this is telling me is about the linear term that is, so it's basically missing out a lot of information that is present in the retarded correlator, and only picking up the piece that is linear in omega, in the small omega limit, and that is my symmetric correlator. Okay, so.
But I don't understand. I think this relation is completely generic for all omega, no?
No, this is true only in the limit omega goes to 0. I should have written it over here, but this is only valid in the hydrodynamic limit where my omega is small.
You mean there's some kind of posh there otherwise, right?
Right. So let me say that I don't have a very good answer for what happens if my quantum fluctuations are also taken into. I mean, this talk was purely focused on statistical fluctuations. I don't have a very good answer for it, but I suspect that this relation, the way it is written over here, won't be true anymore.
Okay.
So I think what's going on here, if I say something.
Yeah, sure.
Is that, I mean, in quantum field theory in real time, right? You can take the Kähler-Lehmann spectral representation, and then all of these Green's functions will be related through the spectral function and analytic continuations. Then when you go to an equilibrium thermal state, this analytic continuation has a special form, which is called the fluctuation dissipation theorem. And it relates the symmetric Green's function to the retarded Green's function in a particularly simple way.
Right.
With just a prefactor, which is hyperbolic cotangent of the temperature and frequency. And now you took the small frequency limit of that hyperbolic cotangent. That's why it's only true in the small frequency limit.
Okay. But
I think that's what's going on. So
Yes, I understand now. I understand what you're saying. But
of course, you can always express them in terms of the spectral representation. And one of these sites is the spectral function, right? Which, for example,
that does not seem to be true anymore if you include the stochastic fluctuations.
I guess, yeah. So you're saying that then you break
because the cotangents. This is trivial. This just comes from summing over the Matsubara frequencies in the
that's right.
And the rest is just the retarded Green's function.
Mm-hmm.
But then the retarded Green's function in the static limit is analytic in K, but then the symmetric one does not seem to be analytic in K. So this relation must break down if you include the stochastic fluctuations in this way, right? And that seems strong because this is actually the full, as you say, this is the fluctuation dissipation relation, right?
Yeah, I see what your point is. Unfortunately, I don't have a quick answer right now. All I can say is that the symmetric correlator itself is not constrained by any causal response properties and stuff. So that being non-analytic in the static limit is fine. But I have a feeling that it's something to do with the omega goes to 0 limit of what Sasha was also pointing out. Mm-hmm. And there it might be possible that in omega goes to 0 limit, it's fine for we want to have the retarded correlator to be analytic, but it's fine for the symmetric correlator not to be analytic.
Yeah, so we know that there are happy examples where the symmetric, where the spectral function is non-analytic, right? For example, if you take 0 temperature CFT at finite omega, finite k, in 4 dimensions, the result is log of k squared minus omega squared. So of course there's a branch cut both in omega and k plane that goes all the way to infinity. So there are such cases where it's easily non-analytic. Or you go to a Peskin and Schroeder, and then you have a mass state, and then at 2 times mass squared you have a continuous spectrum of bound states. So again, it's non-analytic. there's a cut. Right. So in general, that's allowed. Yeah, nothing prevents.
Yeah, that's true. But here the claim is that this non-analyticities remain in the thermal state. These are fluctuations around the thermal state, as far as I understand.
Yes. Yeah, so here it seems like a special statement. Yes, I agree. It's interesting. Yeah, it's very interesting.
Can I ask another question? I dimly remember this MSR formalism, this Martin Siegel-Rosa. So there's a way of writing this as a sort of almost like a topological field theory, where you have also some fermionic fields and you have some fermionic operation, Q operation, which is nilpotent, etc., etc. Does this bring any insight or additional? Can you? Because here it didn't seem to play any role in your.
Right. So my talk was primarily focused on the Schwinger-Keldysh formalism. I mentioned the stochastic approach just to show that it was kind of an intermediate step between the linear response theory, which kind of ignores all nonlinearities completely, and the Schwinger-Keldysh approach. So that's why I flashed a few of those results. Now, that being said, if you are working with the stochastic approach, and you do with, and one of the questions was, I think, asked, where is it? Yeah, and if you look at this effective action, for example, this C is proportional to D times chi. And if you, for example, say that my transport parameters, D, which are functions of underlying chemical potential and temperature, etc., and if there are fluctuations in mu and T, then there should be fluctuations in D and chi, etc., that are sitting as coefficients in this effective action. If you expand them about their equilibrium values, you start generating some interaction terms here as well. So that is one way to do that. And it turns out that as far as if you are interested only up to quadratic order in the noise fields, then the action that you will generate is same as the action that you compute using the Schwinger-Keldysh approach. Okay, so the stochastic approach is not all that weak, but it's a major drawback that you don't generate terms which are higher than quadratic in the noise fields. For example, here again, as far as this talk is concerned, I truncated everything up to quadratic order in the noise fields as well, but you can in principle go beyond the quadratic order. Okay, but that is not even in principle allowed in the in the stochastic approach. So that's one major shortcoming of that, which I wanted to point out. I hope it makes sense.
But Ashish, I think at the tree level, I mean, well, when you consider only the free Lagrangian, the Schwinger-Keldysh result is nothing but the one you found from a stochastic hydrodynamics. For example, the first line in the, yeah, do you agree with this?
I agree.
Okay, good.
Yeah.
Okay, so phi A field in the first line is the same as rho field in your stochastic part.
Exactly.
Okay. Now, if the experts don't ask more, I can ask a couple of very easy questions. So, I thought when you talked about the non-analyticities, I thought you were going to interpret them physically, but then you said that they were just the product of having chosen bad the state you're starting to perturb, right? Because KMS is equivalent to starting with the honest equilibrium state.
Right.
So,
so the best
is this the right way of looking at it, or because, for example, if you have non-analyticities, it could be because you have some effectively massless degree of freedom in the system, or you have some threshold, like for example, the degree of freedom that you are using actually decays, and you can have some threshold, like what was commented before about bound states, etc. So is it obvious that I have to dismiss the non-analyticities as unphysical?
No. So as far as our intuition was concerned, it was coming from the equilibrium generating functional, and the fact that in thermal equilibrium, we want our correlation functions, the retarded correlation functions, to be analytic. Otherwise, thermal screening won't work. So our physical intuition was
coming. So you are assuming physically that the static correlation functions are gapped.
Exactly. So I have a finite static.
But it could be that you have a system in which they are power-like, for example. Is this kind of forbidden?
No. In principle, they're not forbidden. But all I can say is that it will require a totally different approach. For example, let me just say that if I was near a second order critical point or something where this correlation length itself diverges, here my physical criterion that on which I built upon my analysis was essentially that my correlation length is finite and I'm probing the system at scales much larger than this length scale. But if that's not the case, then I have to associate or introduce degrees of freedom associated with those fluctuations as well, and then construct my effective action and then carry out the entire analysis again. So this has, I mean, the physical intuition here was coming from having a finite correlation length in my system and then probing it at scales larger than that. But if there are other considerations, other massless degrees of freedom, as you mentioned, then I have to put them into my effective action as well.
Mm-hmm. Okay. All right. Are there more questions? If not, I would like to thank Ashish again. Thank you very much.
Thanks.
I will stop the recording now.
Yeah, thanks for the excellent questions.